Hello everyone, welcome back. In the last video we were going over this problem. We went over A and B, now it's time to go over C. And C is it's much like B, except this time they want the pH at 1/2 the equivalence point. And so to remember, here they wanted at the equivalence point. We said at the equivalence point, that's where you've added equal amounts of moles of your base and your acid. So if you're titrating an acid and you're adding base, at the equivalence point, you have added the equal amount of base to the acid to neutralize all of your acid. And so at the half equivalence point, or the 1/2 equivalence point, that's where you've added half the amount of the equivalence point. So instead of adding one full amount, you haven't added enough to neutralize all of your acid. So instead of the full amount, you've only added half. So in this case, if you remember from part A, we calculated that the total number of moles of your acid is 4.00 times 10 to the negative 3 moles of your HNO2. So to reach the 1/2 equivalence point, that means you add half of that amount in terms of your base. So that means we've added 2.00 times 10 to the negative 3 moles of your KOH. So if we do a stoichiometry table here, where we figure out how much is left after you've added that amount. So remember, the KOH is a strong base. It's going to react completely with the acid, and then we'll look at what's left over. So before you added, we had 0 amount of OH minus. We had 4.00 times 10 to the negative 3 moles of your acid, and you had 0 amount of your NO2 minus, or very, very little. So now we're adding KOH. So we're adding OH minus, and we're adding half of this amount. So half of this amount is 2.00 times 10 to the negative 3 moles of your OH minus, or KOH. We're not really adding any more of this, or this, or this. So then, now what happens after you add it? So because this is a strong base, this is going to react completely with the equal amounts of this. So 2.00 times 10 to the negative 3 moles is going to react with 2.00 times 10 to the 3 moles of your weak acid. So when that happens, you're going to have 0 amount of OH left, and you're going to have subtract this from this, and you get 2.00 times 10 to the negative 3 moles. And then because you reacted with half of this, and you got 2.00 times 10 to the 3 moles, then because of a 1-to-1 relationship here, you react this amount here with this, you're going to produce the same amount in your nitrate ion. So you're going to have 2.00 times 10 to the negative 3 moles of your nitrite ion. So now we have, after everything has completely reacted, you have 2.00 times 10 to the negative 3 moles of your acid left, and you got 2.00 times 10 to the negative 3 moles of your conjugate base. So now we can use the Henderson-Hasselbalch to find the pH. So again, Henderson-Hasselbalch is the pH is equal to the pKa plus the log of the concentration of the base over the concentration of the acid. And so we need to figure out what the pKa is again. So the pKa again is 3.34 So this is equal to 3.34 plus the log. And then the base over the acid, well, this is the base, and they're equal. So the base over the acid, so this is going to be 2.00 times 10 to the negative 3 moles over 2.00 times 10 to the negative 3. That's the same as 3.34 plus the log of 1, right? Because this is equal to 1. And so, because it's equal to 1, the log of 1 is 0. So this is equal to 3.34 plus 0, which is equal to 3.34 for the pH. So that is the pH of the solution after you reach the 1/2 equivalence point. Okay? So I hope this was helpful. I hope you enjoyed the video. If you like my videos, please like, share, subscribe, hit the notification bell, and make a comment in the comment section. Thank you for joining me, and I'll see you next time.